We've seen the practical way of solving the Towers of Hanoi problem. Let's just restate it before we start to look at it in a programmatical type of way. Oh, so what's the problem? Well, the problem is we need to move disks from one tower to another. In other words, what we're doing is moving from stack A to stack C. Okay, and the rules? Well, the rules. Only the top disk can ever be pushed to or popped from a stack, so you can only ever manipulate one disk at a time. And it's got to be the top disk. Okay, and the larger disk cannot be placed on top of a smaller disk. Okay, so given that, let's have a little look at a programmable approach to it. So Towers of Hanoi, stacks approach moving disks from one rod to another, or from one tower to another. Let's have a look down here to begin with. Well, just to ensure that I know how many moves are going to be made, I have my calculation. So moves equals 2 to the power of disks minus 1. Okay, and up here we've got an input for the disk. So disk, it was int input, how many disks. And so with that value I can then calculate the number of moves that are needed to be made. Now, I don't have to have that in there for the program, but I like to show it to me so I know how many moves it's likely to take. Let's have a think about this. What do we need? Well, we've got a function. We've got a function called Tower of Hanoi. You could shrink that down to TOH, or T, I suppose. And we've got 4 parameters in there. We've got disks. Now, we get the value for that from the user input. Of course, you could fix it, but I like to have a little bit of interactivity. And we have 3 towers, A, C, and B. A is the tower, or the stack that we are moving from, or popping from, if you like. And C is the destination stack, where everything will be pushed to. And B is used as an intermediary or a temporary stack to hold things as we're moving about. Okay, so armed with that, what have we got? Well, let's have a look at our function. We'll open our function. We've got Tower of Hanoi disk ACB, which is just feeding the parameters from the bottom there. Okay, and we've got a little check. We've got a little iterative statement here. If disk is equal to 1, print pop disk 1 from rod A and push to rod C. So let's just check that out. Let's hit F5 and see what happens. Okay, how many disks? Well, if I say 1, there we are. The number of moves equals 1, of course it would. It's a trivial problem, of course. Pop disk 1 from rod A, push to rod C. Okay, so that's fine. Let's see what happens if we get beyond 1 disk though. Well, down here we have the function call, disks minus 1, so it reduces 1, and it will go A, B, and C. So we're using those parameters. Now notice that they're in a slightly different order. That's important for our recursive call, because our recursive call, really all it works on are all the disks above the bottom disk. So if I have 3 disks, it'll do the majority of the movement on disks 1 and 2, and it will only move disk 3 once. Same for if we had 4 disks, same if we have 5 disks, and we'll test that out in a second. Okay, so in my program, I like to have feedback going on. So I've got input, press return to continue. So what will happen is it will give me my first move, and then wait for me to hit the return key to get the next move, then the next move, and the next move, and the next move. Notice that our recursive call down here uses a similar formula, disks minus 1, but now it reverses, or changes rather, the order of the towers, and we need that so that our movements can be tracked. Let's run it with more than 1 disk in it. So F5, there we go. Just waiting for that to wake up. There we go. So how many disks? Well, if I say 2 disks, okay, so the number of moves is 3. Alright, so I'm going to pop disk 1 from rod A and push it to rod B. Okay. Pop disk 2 from rod A, push to rod C. Okay. And then pop disk 1 from rod B to... Yeah, okay. So, now bear this in mind. So with an even number of disks, I start off with pushing from rod A, and popping from rod A rather, and pushing to rod B. Let's try with an uneven number. Okay, how many disks? So let's go for 3 this time. Okay, so the number of moves equals 7. Well, that fits my formula. Now I'm popping disk 1 from rod A and pushing to rod C on this occasion, and then disk 2 from rod A, pushing to rod B, disk 1 from rod C, pushing back to rod B, disk 3, and so we can see the point here. There we go, and that's our moves. So now we know that our program, if it's an even number of disks, it will start with rod A to rod B. If it's uneven, rod A to rod C. Well, let's double check on that. Let's try it with 4 moves, or 4 disks rather. So F5, how many disks? 4. There we go, push from A to B. So I'm just going to run it again, this time with 5, just to be double sure. I'm double checking on my code. So how many disks? There we are, rod A to rod C, and we can see that uneven is rod A to rod C, even is rod A to rod B, pushing and popping, or popping and pushing rather. Okay, so let's just get rid of the output there. So very simple program to show you how Towers of Hanoi works as a recursive program, and it allows us to investigate how stacks work. We can undertake the Towers of Hanoi in an iterative process, but the problem becomes much more complex when you do that. I'm just flashing the code up here for you to see. So we've got a number of functions there, but we've got a number of really quite complicated if statements here, because it's an iterative process. It needs to check the position of all the disks every time. So recursive or iterative, well, my money goes for recursive because it's a much simpler program. Okay, thank you.